Imae from Hiroshima University, Japan. Okay, so before giving the wonderful presentation, I would like to introduce his biography. He received the bachelor, master, as well as the doctoral degrees in engineering from Osaka University. It is located in Osaka, Japan, in 1992, 1994, as well as 1997, respectively. So during his doctoral course, he worked as the research fellow of the Japan Society for the Promotion of Science for those years, 1994 to 1997. In 1997, he joined with the Japan Advanced Institute of Science and Technology, ISWAGA. Then, as the assistant professor since 2006, he is an associate professor of Hiroshima University, Hiroshima, Japan. Also, he worked as an adjunct lecturer of Muroran Institute of Technology and a visiting professor of Hiroshima University of Science and Technology in 2018. His topic is electrochemical control and the quantification of carrier density of π-conjugated polymers. Dear Professor, now the stage is yours. You can start the presentation.
Thank you very much, Chairman. Can you hear me?
Yeah, sure.
Okay.
You can start the presentation.
Hello, everyone. My presentation was originally scheduled from 10:20 a.m. to 11 a.m. GMT time. However, due to significant delays in the previous presentation, I now only have a few minutes left. Or rather, my presentation time has already passed. Therefore, I won't be able to cover much. If you would like to know more about my presentation, please feel free to email as shown here. The conducting polymers were discovered by Professors Shirakawa, Hige, and McDermott. These polymers not only exhibit electrical conductivity, but also possess unique optical, electrochemical, and electrical properties. Therefore, they are applied to a wide range of electronic devices, such as solar cell, transistors, and light-emitting diodes. And even now, they are still being actively studied. For these achievements, the Nobel Prize in Chemistry was awarded to them. The conducting polymer developed by Professor Shirakawa is known as polyacetylene, as shown here. This is a pi-conjugated polymer where pi electrons are conjugated along the backbone. Subsequently, based on this structure, many types of conducting polymers such as polysiloxane, polypyrrole, and polyphenylene have been developed. Furthermore, by introducing various side chains into these polymers, side chain engineering not only influences the polymer's solubility but also its optoelectronic properties, thus expanding the research field of conducting polymers. However, these polymers exhibit semiconducting nature in their neutral state. To exhibit electrical conductivity, these polymers require a doping process, which injects the charge carrier into the polymers to facilitate the flow electricity. In order to inject the charge carriers into these neutral polymers, there are two major types of doping techniques. One is chemical doping, which injects electric charges through a chemical reaction using an oxidizing or reducing agent. This method is very simple, but it can be difficult to precisely control the doping state and accurately quantify the charge carrier density. The other is electrochemical doping, which injects electric charges from electrodes through electrode reactions. With this method, the doping state can be precisely and freely controlled by the applied electrode potential, and the charge carrier density can be accurately quantified by measuring the amount of electricity generated during doping by using coulometer. Therefore, we utilize an electrochemical method to control and quantify the charge carrier density of π-conjugated polymers and analyze the correlation between their charge carrier density and electrical properties. So, in today's presentation, at first, I will introduce the method to control and quantify the charge carrier density of π-conjugated polymers using electrochemical method and its application to the investigation of the charge transport and some electric properties. To estimate the charge carrier density of π-conjugated polymers, we utilize the potential step chronocoulometry, PSC, which is a kind of electrochemical measurement. Here I explain this method using poly-3-hexylsiphene, P3HT, as a typical example of π-conjugated polymers. For the PSC measurement, we needed to understand the redox properties of the polymer. So before the PSC measurement, cyclic voltammetry is carried out using a 3-electrode system. In this system, an ITO platinum plate coated with the polymer is used as a working electrode. Here I show the cyclic voltammogram of the P3HT film obtained by this system. At minus 0.4 volt, no current is flowing and P3HT is in neutral state. When the potential was shifted to the positive side from minus 0.4 volt, anodic current was observed from around 0.2 volt. It suggests that the P3HT is oxidized in this potential region. When the potential is reversed to the negative side from 0.8 volt, cathodic current was observed. It suggests that the electrons were returned into the oxidized polymers. Finally, when the electrode potential drops to around 0 volt, the electrons are completely returned to P3HT and no current was observed anymore. And then P3HT returned to a neutral state. Based on the information obtained from the cyclic voltammogram, the charge carrier density of P3HT can be estimated as follows. At first, the electrode potential was set at minus 0.4 volt. At this potential, P3HT is in the neutral state. Then the P3HT film was oxidized at a certain potential by stepping the potential from minus 0.4 volt, and the amount of electric charges generated during the oxidation process was recorded by the coulometer. And finally, the charge carrier density can be calculated from this equation using the amount of electricity estimated from PSC analysis, the elementary charge, and the film volume calculated from the film area and the thickness. By applying the technique for quantifying charge density using PSC method, we analyze the same electric properties of conducting polymers in relation to the charge density. We are consuming a lot of primary energy to power plants and automobile and some factories. However, only 34% of these energies were efficiently utilized, but most of the others were wasted as a large amount of heat energies. To recover these heat energies, thermoelectric conversion system is attracting a great deal of attention, because this system can directly convert these wasted heat energy to electric energy and can produce a great deal of electric power. Thermoelectric system can produce electric power based on the Seebeck effect, which was discovered by Thomas Seebeck. When the temperature gradient are applied to the materials, including electric charges, these charges move to the colder side and finally form the electric field. Thus, the voltage difference is formed between them proportional to the temperature gradient. This proportionality constant is defined as the Seebeck coefficient. Using this character, some thermoelectric materials based on inorganic compounds are already applied to space probes such as Voyager and Cassini, with roasted and a unique battery charger using the thermal energy of campfire. Recently, thermoelectric materials based on organic compounds are attracting attention due to these advantages: low cost, low toxicity, abundance of raw material, flexibility, solution processability. From these advantages, the number of researches on organic thermoelectric materials are increasing since the first report was published by Professor Toshima and Professor Yang. When we discuss on the performances of some materials, we use the dimensionless figure of merit, ZT value, as an index. The higher ZT value means a better high performance. And this ZT value is introduced by this equation, that is the product of electrical conductivity and the square value of Seebeck coefficient divided by thermal conductivity. And as I mentioned before, organic compounds have these advantages. And in addition, organic compound has a nature of low thermal conductivity, and this nature can act as an advantage for leading to the high ZT values. In contrast, electrical conductivity and Seebeck coefficient of organic materials are relatively low. Therefore, we need to improve these values for practical use of organic thermoelectric materials. It is already known that the electrical conductivity is expressed by the product of densities and mobilities of charge carriers. So in order to enhance the electrical conductivity, increasing the density or mobility of charge carrier is crucial. When it comes to the Seebeck coefficient, such an equation has been already proposed for inorganic thermoelectric materials, and it can predict a straight line in a log plot of the Seebeck coefficient against charge carrier density. However, such a correlation has not been proposed for the organic thermoelectric materials because of their short history. We expect that the PSC method can be applied to the investigation of the correlation analysis of Seebeck coefficient with charge carrier densities. To demonstrate the possibility of this research, we evaluated it using P3HT. The doping level increased with increasing the electrode potential, and electrical conductivity linearly increased with increasing the electrode potential, and electrical conductivity linearly increased with increasing the doping levels, and finally saturated at around 20% of doping levels. On the other hand, Seebeck coefficient decreased with increasing the doping level. This phenomenon is a typical trade-off relationship that can also be observed in inorganic thermoelectric materials. It was found that the dependencies of these factors on doping levels were not affected by the chemical structure of the dopant ions. Interestingly, it was found that the log plot of Seebeck coefficient against doping levels showed a good linearity. In order to investigate the effect of doping method, P3T was chemically oxidized using nitrosonium hexafluorophosphate. The doping levels were changed by controlling the time of dipping the P3T film in a solution of NOPF6. The doping level of chemical oxide P3T films were estimated by PSC method. It was found that both dependencies of the electrical conductivity and Seebeck coefficient against the doping levels were similar to those of electrochemically oxidized P3HT, even though the doping method was different. Professor Crispin also reported the dependencies of thermoelectric properties of P3HT chemically oxidized by NOPF6. However, these tendencies are completely different. In our case, the electrical conductivity linearly increased at low doping level region and were saturated at around 20%, and the Seebeck coefficient showed a good linearity. On the other hand, in the Crispin's report, electrical conductivity just increased linearly and were not saturated even at higher doping levels. And the dependencies of Seebeck coefficient showed a S-shaped curve. Why these differences are observed? At present, we think that these differences were formed by the different estimation method of doping levels. In our method, we can directly estimate the amount of electric charges in entire film. On the other hand, Crispin uses the explicit analysis and estimates doping levels using the ratio of the intensity of phosphor and sulfur signals. However, XPS analysis is normally used for the surface analysis of materials, and the average depth is around 10 nanometer. Thus, it is possible that the XPS analysis cannot adequately reflect the doping level of entire films. Okay, I skip this area because there is no time. And I summarize my talk. Doping level of conducting polymers could be precisely controlled and quantitatively estimated by potential step chronocoulometry. The electrical conductivity increased with increasing doping level and finally reached saturation. The Debye coefficient decreased with increasing doping level and showed a trade-off relationship with electrical conductivity. A good linear relationship was obtained for the double logarithmic plot of Debye coefficient and doping levels. A variety of novel polysilophane was synthesized by controlling the structure of side chain groups and the incorporation rate of the side chain groups. But this content is skipped in today's presentation. Sorry. So the further information can be given by through the email. If you are interested in my talk, please send an email as shown here. Thank you very much for your kind attention. And finally, I introduce you to a special journal issue focusing on related themes. I'm honored to serve as a guest editor for MDPI's Materials Journal, responsible for a special issue titled Advances in Pi-conjugated Organic Materials for Energy, Biomedical and Environmental Devices. This issue highlights the latest advantage in pi-conjugated organic materials for energy, biomedical application, and environmental devices. I am eagerly awaiting submissions from researchers and engineers worldwide. Sharing their research findings in this special issue could lead to further advancement in these fields. For more details on submission guidelines, please visit the Materials Journal website. This is a great opportunity for your research to have a significant impact on the global scientific community. If you are interested, I encourage you to consider submitting your work. Thank you once again for your attention and consideration. Okay, thank you.
Thank you so much, Professor. You have given the hello.